Hello, good evening, and welcome to Computational Thinking at IBA. My name is Jawwad Farid, and I will be your instructor and facilitator for the next 14 weeks on this journey of discovery and exploration. The course is essentially a series of experiments designed to provoke questions that you should be asking yourself as students of computer science. Let's start with the first question. What does it really mean to think? When a machine does something intelligent, do we believe that it is capable of thinking? And then thinking leads to more interesting, deeper, subtler questions along the lines of, if it can think, can it also feel and sense and know and understand and comprehend? Let's try a very simple experiment. If I put this image in front of you, what's your first reaction? When I pose this question in my classroom, I get three different kind of responses. I think the first response, the most common response, is that when I see this image, it reminds me of my trip to the northern areas, and I feel peaceful and comfortable and serene. I have a second response, and that response is, I feel very small when I look at myself compared to the size of this majestic mountain. And there's a third small, which is I feel scared and lost. These are all three normal natural responses, and they're linked essentially to your experiences, your association with memories of mountains with snow on them. Where do these reactions come from? Is that years of training? Is that exposure? Is there some kind of natural programming? Is there a genetic code that helps us, that makes us react a certain way when we see mountains or nature for that matter? If I switch this image from the mountains to this shot of a bird standing in a lake, does your reaction change? You're likely to not have exactly the same response that you had to the scene of the mountains, but you're still likely to have some response. Where does that response come from? What if you come from a part of the world where all mentions of mountains and birds by the lake have been eradicated? They become what we'd call non-mentionable in your part of the world. Nobody's ever described a mountain to you. You've never heard that label. You've never seen a mountain. And we meet and I say, I feel peaceful and comfortable and serene when I stand in front of mountains. I'm amazed by their majesticness. I feel amazed, serene, peaceful, and at the same time I feel very, very small in terms of nature's power and bounties. How would you know what I mean? If you extend this line of thinking, a natural question is, what comes first? Our ability to label things or our ability to think about them? Language or thought? Expression or thinking? Context, meaning, or knowing? And how do you find the answer to this question? I don't have an answer for this question, but I would like you to think about this at a deeper level so that you have an opinion and that you can back that opinion up with data and valid information. Let's try another experiment. This experiment starts off with a lovely poem by Faiz Ahmed Faiz, very famous, very well respected poet from Pakistan, who spoke about multiple themes, and one of the themes was freedom of expression. So, Bol ke lab azad hain tere, if you think in terms of literal translation, essentially says, speak for your lips are free. Bol zaban ab tak teri hai, speak for the tongue or your voice still yours. Question is, when I say bol ke lab azad hain tere and I translate that into speak for your lips are free, what's the underlying process? How does that process work? And if a machine, so if you plug this line into, let's say, Google Translate, if a machine is able to translate this verse into its equivalent expression in English, is the machine capable of thinking? And when the machine translates that verse, bol ke lab azad hain tere, into speak for your lips are free, does the machine understand the weight of these words, the meaning of these words, the context in which these words were written? Today, in 2024, the answer is no. That's my opinion. Some point in time in the future, the answer may become yes. But as of yet, as of now, a great deal of discussion and debate as and when this specific event would happen, when machines would be able to sense, to know, to understand, to comprehend, to become self-aware. We call that specific event singularity. But today, as of 2024, despite the fact that we have many magical tools and technologies available that'll convert this gorgeous, beautiful poem by Faiz into an equally lovely expression in English, this is not possible. We don't think machines can sense, feel, understand, know, comprehend, or sense what they're doing. Switch from Urdu to Japanese, slightly different language, and you see a different expression. So Urdu, some of you may have seen, mainly because you come from a country where this is the primary language. You may have heard of Bol because Nayyara Noor sang it, Tina Sani sang it, many other singers sang Faiz's lovely verses. Must have heard Bol Ke Lab Azad Hain Tere in many, many forms. There are TV channels, there are films, there are videos, there are movies, there are music videos that use the same theme. But Japanese is different. Especially in the Indo-Pak subcontinent, the exposure to Japanese is limited. There are people who still use or create or try or have a sense of what this word means. But in a room of, let's say, 200 people, there may be about maybe 3 who would understand the context of this specific symbol. Symbol stands for mindfulness, sense-making, being aware of context. But if you have not seen this before, your first natural reaction would be, I don't know. And even this I don't know is an evolved natural response that you've been trained to generate when you see things and you see elements or symbols or dimensions that you don't understand. I don't know is a valid response to stimuli to something you have never seen before. But unlike mountains and pelicans, you don't feel majestic, you don't feel in awe, you don't feel serene and comfort. You simply feel, I don't know. I don't have all the answers. So when people ask me about what is computer science, I tell them computer science is the language of solving problems. When you become a computer scientist, you acquire a skill set which makes it easier for you to attack problems and solve them. We're not speaking about specific languages. We're not saying, you acquire or you learn to write code in C, C++, Java, or Python. We're talking about a much broader assessment, much broader concept of looking at the entire field as something which is dedicated, which is devoted to solving problems. Take the example of our poems. On our previous pages, I gave you 2 poems. Take the example of poems. In our previous instance, we saw Faiz's lovely poem of Bol Ke Lab Azad Hain Tere. I have another one. Habib Jalib, another famous, respected, well-regarded poet from Pakistan, who wrote, Zulmat ko ziya, sar sar ko sabah, bande ko khuda kya likhna. Now, if you don't speak Urdu, you have no idea what I've just said. We have some sense of the first one. So, the first poem number A, Bol Ke Lab Azad Hain Tere, we've translated that, speak for your lips are free. But when I refer to the second poem, which is Habib Jalib's poem, just as famous as Bol Ke Lab Azad Hain Tere, this poem starts by Zulmat ko ziya, sar sar ko sabah, bande ko khuda kya likhna. You have no idea what this means if you don't speak the Urdu language. So if I asked you to translate this using, let's say, Google Translate, where would you start? So the challenge in specific instances, translate these 2 poems using a translation tool available to you so that you have the equivalent result in English. Your first step would be to actually break this down into a smaller problem. The smaller problem would be to say, I'm not going to translate the full poem, I'm going to start by verse. So the first verse for me in Bol was Bol Ke Lab Azad Hain Tere, and I've done that, right? It's speak for your lips are free. I have a similar verse on this side, which is Zulmat ko ziya, sar sar ko sabah, bande ko khuda kya likhna. How do I translate this? Once again, in the field of computer science, if you think in terms of divide and conquer, breaking larger problems down into smaller problems, you've just broken a much larger problem, couple of verses, into a simpler problem by only focusing on one verse. But now we can break that verse into a single token, and that token is Bol. Think about the process we use to translate Bol Ke Lab Azad Hain Tere. How does that actually work? You start with the first, very, very first word, which is Bol. What does Bol stands for? Now when I say what is BOL stands for, the underlying implication is that somewhere I have access to a dictionary, a lexicon, that has a list of relevant words that are relevant to the verses I have in front of me, and I can walk through them to figure out what the right verse is. So for instance here, when I say BOL, I know, because I'm a speaker of the Urdu, because I speak both Urdu and English, I know that the relevant word, the matching word, the relationship that needs to be established is between BOL and speak. So BOL literally translates into speak. And then I repeat this process step by step for every other word in the verse in front of me. So BOL translates to speak, K translates to for, lab. So K, this is K. BOL K, so K translates to for, lab translates to lip, azad translates to free, hai tere is yours are. And you now actually have a translation. And the translation is yours are free, lips for speak, which doesn't make much sense because it's not structured correctly. So you now need to apply some kind of structure. So just doing a lookup, a straightforward dictionary lookup, is not enough for you to actually end up with a reasonable translation. Reasonable translation, not as poetic as the original Bol ke lab azad hain tere, is speak for your lips are free. So we've moved things around a bit so that the structure of the English translation is in alignment with the beauty of the original Urdu verse. Speak for your lips are free. Bol ke lab azad hain tere. Now if a machine were to do this correctly, so for example, if you took this verse, plugged it into Google Translate and looked at the answer, and the answer was speak for your lips are free versus yours are free lips for speak, does that mean the machine is capable of thinking? And even if you had a translator that actually came up with speak for your lips are free, the correct poetic structure, does the machine get the context? Does the machine understand, comprehend the meaning of the words? Does it understand the weight of the words? Once again, as I said earlier, the answer is no. But this sort of gives us a sense, it breaks down the process that we've been thinking about. How does computer science work? When we see computer science as the language of solving problems, we see that languages and problems both have nuances, have subtleties. It's not enough for you to learn how to write code. You also have to understand everything else that happens around that process. What is this everything else? So one part is language, one part is grammar, one part is syntax and rules, but more important part is semantics and context. So when we see Bol ke lab azad hain tere, says speaks for your lips are free, but what context did Faiz write these verses when he originally wrote them? Or when Faiz wrote Hum ke thehre ajnabi, or when Jalib wrote Zulmat ko ziya, sar sar ko sabah, bande ko khuda kya likhna, what was the context? What was the historical context that led to those words? This context, this understanding of meaning and knowing is also part of the process. And I think right now, when we think in terms of computer science, when we think in terms of intelligence, when we think in terms of artificial intelligence or machine learning, we've knocked language out. We can do language very well. We understand grammar because we can specify that with rules. We understand syntax, again, because we understand rule. Semantics and context, we've come a long way. So we can discern, we can dissect, we can identify, we can extract context and meaning from a wide collection of words, books, paragraphs, and writings. Meaning and knowing, though, is a very, very different level of intelligence, very, very different level of thinking. And I think you'd see, you would feel when you speak to 5 people in the field, you would find that some would say that we have this, that we've arrived here, while others would say no, we are far away from it. But despite this divergence in opinions, I think all of us today agree and accept, even though we might not say this publicly because it would go directly in conflict with our public stance. Machines right now are not capable of understanding, they're not capable of thinking or thought, and they're not capable of expressing their opinions or their feelings because they don't have feelings. So within the context of computer science then, there are 2 separate debates. that we've just triggered with this discussion. I think the first debate is, think in terms of language of solving problems, what does that require? We've got two parts, all the way from language to semantics, and I think we get that. The second part that deals with meaning, knowing, understanding, thinking, and expression, we don't have as good a sense of this. The second debate is what part of this challenge, of this problem, this issue, are machines capable of, what part they're not capable of. Whatever opinion we have today on both of these debates will change. I think this is something that we have to accept. It'll change every minute going forward into the future. It'll change because that's what technology is all about. Change is good. We understand it. We accept it. So it's okay for you to have an opinion that changes. It's okay for you to keep an open mind, because as you see new evidence, as you see new data, as you see new experiments, as you see new results, it's possible that even my mind with respect to what machines are capable of today will change tomorrow if I see the right evidence. And the same should hold true for you. What does problem solving involve? 4 things with respect to the context of this course. First is goals and objectives, intent and purpose. What are you trying to do and why are you trying to do it? What are the resources we have available? What are the limitations and restrictions applied on us? What is our prior history of doing this? There are many more dimensions to solving problems, but these 4 are the ones that are of interest to us. Now, when you combine these 4, there is an alternate perspective, an alternate view that comes forward, and that view is, think of problem solving as a search challenge. So, when you search for Jawwad Farid or IBA or Faiz Faiz or Habib Jalib or Bol Ke Lab Azad Hain Tere on Google search, what are you doing? You're telling Google, this is the keyword that I want you to find an answer to, or related answer to, or content or context around this specific keyword. What if we approach problem solving with the same lens? Think of problem solving as finding a solution in a large problem space. And that problem space, again, for simplicity, is defined by 3 dimensions. The first dimension is domain, subject matter expertise, background, context. One dimension is what's the desired end state. One dimension is resources and constraints. And then what do? We take this dimension, which we call a problem space, and we search for solutions in a related solution space. Essentially what you're doing when you talk about problem solving, or essentially what you're doing when you try your hand at computer science, you're trying to build a bridge from the problem space to the solution space. The challenge though, and it is a challenge, is that there is not a single solution. There are multiple solutions. How do you evaluate which solution is the best possible solution? So when you start looking for bridges, you'll find that there might be 7 or 8 or 9 or 10, or sometimes even an infinite number of possible paths to the solution that you're seeking. How do you know which solution is the right solution for you? Which then leads us to a rubric, right, or evaluation criteria that we can use to assess the quality of a solution. And 3 that we propose, again, with respect to the context of this course, with computational thinking, with ITC, with respect to the fact this is your first semester in IBA, the 3 dimensions that we're interested in. One, the first dimension is efficiency. How efficient is our approach and our solution? Our second is effective. Does it do everything that it has to do? And then a third and final dimension is elegance. So if you looked at our translation attempt at Bol Ke Lab Azad Hain Tere, our original translation was Bol, speak, for lips free are yours. Now, it may qualify as an efficient translation, but was it effective? No. Bol Ke Lab Azad Hain Tere, speak for your lips are free, is a far more effective solution to the problem. The first one is efficient, but it's not effective. And it's certainly not elegant. Speak for your lips are free is elegant, is efficient, and effective. So when you think in terms of paths, think in terms of translation paths. Translation paths that take a problem statement from a problem space, map it directly to a solution in a solution space, and then you evaluate whether that's the right path by looking at elegance, efficiency, and effectiveness. And that's the key part, the key theme that we explore and discover in this specific course. I'm in well to talk about poetry, but what does problem solving involve? If I take the language, grammar, syntax, semantic, context, meaning framework and structure around languages, and I apply that to the language of problem solving, how would that work in the problem solving domain? So I think the first part, the first challenge, right, that maps directly to what we call grammar or syntax is enumerate, count, or map the problem space. I think the second step is analyze it. Third step is design. The fourth step is validate. The fifth step is building. So when somebody comes to me and says, I don't want to be a computer scientist because I don't see myself as a programmer, I tell them, listen, programming is many things. Computer science is many things. When you think in terms of just writing code is just one of the 8 things that you have to do when you try and solve problems. You have to map the problem space, you have to analyze it, you have to design it, you have to validate it, you have to build it, you have to field test it, you have to deploy it, and then you have to validate your social contract and the immune response to change that society as a whole has. When you try and change behavior, you will find out that changing behavior is the hardest of things. To be an effective computer scientist, you have to do all 8. Programming is just one of these themes. And beyond programming, I think there is also a common element that you should be able to see. And that common element is debugging. When we analyze, we also debug our analysis or our original mapping of the problem space. When we design, we debug everything before that. When we validate, we debug our assumptions. When we build and code, we debug our code. When we field test it, we debug our assumptions with respect to the deployment environment. When we deploy and execute, we debug our assumptions with respect to engagement with customers and users. And then there's this whole debate around change management. We think just because we build a beautiful, marvelous, technologically superior, sophisticated, and elegant solutions, users and customers and society at large would run to buy it or use it. But that doesn't always happen. So if debugging is this important, then any course that focuses on understanding the language of problem solving should emphasize your ability to debug. How do I teach you debugging in a course which is a non-programming course? Computational thinking is part of a 2-course series. The first course, Introduction to Programming, which is taught by my counterparts at IBA, and that's the programming course. Computational thinking is a non-programming course, so we don't use programming language in this course. How do I teach you to debug if I'm not going to use a programming language? This is a design challenge. I have to figure out how to debug it. How do you think we're going to do this? How do you think we're going to teach you how to debug if we are not going to use programming languages? The answer is what I call a problem set or case background. So we picked up 4 cases that we think are interesting specimens of wide search spaces that have themes that are important for you to appreciate as students. The first is Scrabble. So Scrabble as a game, and we look at both word generation and board evaluation together, sort of covers or fits into the theme of exploring game AI. How does game AI work? Here AI starts for artificial intelligence. Artificial because it's not natural intelligence. And just because a machine is capable of playing Scrabble or it's capable of playing chess, does it mean the machine can think? No. Just like we looked at a lexicon of words, looking up words from that lexicon is not thinking. Similarly, looking up moves, valid moves, relevant moves, right moves, winning moves from a lexicon of moves is not thinking. So that's the first one, right? The first case is Scrabble. We spend a fair bit of time on both word generation and the board evaluation challenge. Our second component is the SBP payment system dataset. Here we take the same sequence of tools and thinking that we've explored and apply them to Excel, but this time we work with Excel pivot tables, because now here, the focus was on simulating, forecasting, generating, mapping solution space. Here the focus is on finding answers from a large collection of data. Then we have a third set of cases that look at design within the context of actor roles and behavior framework. We have a fourth which focuses on matrix multiplication. Then we have a fifth that looks at building a 16-bit CPU in larger sim. And throughout all of these, I think the key theme that we're looking at efficiency, grace, and elegance, and we're looking at your ability to debug. Debug your thinking, with respect to Scrabble, debug your thinking with respect to data set and Excel pivot tables, debug your thinking with respect to actors, roles, and behaviors, with respect to matrix multiplication, efficiency, grace, and elegance, and 16-bit CPU. Why these specific cases? Why this specific model? When we work with students, especially students who are new to computer science, students who have no prior background to computer science, even students who have a background to computer science, I think the biggest common challenge that everyone faces when they start looking at computer science seriously is how do we attack problems. And I think the most powerful tool that we found when it comes to attacking problem spaces is the ability to think sequentially, the ability to break things down and sort them in such a fashion that you can move forward, get closer to the solution. So when we look at Scrabble and SBP payment system, we use Excel. For actor roles behavior, we use Canva. For multiplication, we use Excel and Replete. For grace and elegance, we look at Replete. For the 16-bit CPU, we use Logisim. These 4 or 5 tools, Excel, Replete, Canva, and Logisim, these 4 tools are the playground we'll play in the next 14 weeks. What are we trying to do? What are we trying to prove? What we're trying to do is give you a sense of real-world search spaces. Real-world search spaces are broad and wide. Your results, your solutions, your correct, the solutions that meet the scoring criteria you're looking at, the yield for those solutions grows lower as your search spaces grow in size. So then the key thing for you is to figure out, how do I converge? How do I get to the right search solution as quickly as early as possible? There's a very simple rule: fish where the fish are. You must build a sense of where would I find the right solutions. And as you go through this process again and again multiple times, you build a sense of how to go about doing that. We want you to understand this beautiful quote by Hans Hofmann. The ability to simplify means to eliminate the unnecessary so that the necessary may speak. Our objective by walking you through these cases is to teach you how to simplify, how to identify the unnecessary, how to eliminate, and how to hear when the necessary starts to speak. I'd say that our course on computational thinking is essentially about thinking. It's about exploring paths that you haven't experienced before, about experiences that will hopefully change the way you approach and think. It's about understanding that you need to count, to enumerate, to map problem spaces, that you need to understand boundary conditions, constraints, restrictions, and limitations to create and design solutions. And to do all of this well, you need a model of intelligence that allows you to find solutions faster. So at this point, it's perfectly okay for you to ask, what about ChatGPT and Copilot? Isn't ChatGPT and Copilot and the many such variations of these tools are going to replace programmers all across the world? I have a very strong opinion on this, but I'm not going to say it. I'm going to let David say it. Okay? David works for Meta. Meta is the old Facebook. Meta owns Llama. If Llama is the solution, the be-all, end-all of all our problems on the programming side, why is Llama hiring compiler, low-level performance engineers, especially engineers with expertise in CPU and GPU performance, CUDA, C++, x86, and low-level virtual machines, LLVMs? These LLVMs, low-level virtual machines, have nothing to do with large language machines or large language models. The roles are located in Menlo Park, Seattle, and New York. US work permit is required. My DMs are open for questions. The interesting thing is the date on this. This is not from 200 years ago. This is dated 9 p.m., June 20th, 2024. If generative AI is a solution to all of our problems in the programming world, why is Facebook hiring low-level C++ programmers? That's one side of the debate. There's another side of the debate. Every now and then, shit happens. When this happens, are you going to put your large language model to solve it? You think your large language model can solve this? Somebody has to dig deep into that code to figure out what went wrong and then go in and fix it. Who do you think is going to do that? I don't think LLMs today have the capacity to address this. They can suggest, they can indicate, they can guess, but they can't solve it. That's something that you'll have to figure out on your own. I teach 2 courses at IBA beyond Introduction to Computational Thinking. One is a course on building technology products. One is a course on teaching applied data analysis. In both the courses, But for both of these courses, I think the key theme that we focus on and we emphasize is how do you make things that are better made. The question you have to ask yourself is that when you come to the field of computational thinking, how do you find solutions? How do you find paths? How do you find ideas that stand out from the rest? Now, there is a role that machines may play in that search and in that solution, but you can't get there just with machines. I think you need a higher order intelligence to ultimately find the right path and the right solutions. And a large part of computational thinking is building an appreciation for that higher level intelligence.